Today we will discuss the problems on assignment problem. Let us take this problem. Solve the following assignment problem by Hungarian assignment method. So this is the man and the jobs are given. They are assigning and they given the cost matrix. So this is the cost matrix. Now, before applying Hungarian assignment problem, make sure the cost matrix should be a square matrix. The cost matrix should be a square matrix. So this is a 4 by 4 matrix. So we can apply assignment. We can apply Hungarian assignment problem. So to apply Hungarian assignment method, so we need to remember these things. We need to remember row reduction, how to apply row reduction, column reduction, and allocation. Okay. Now let us see how to solve, how to apply this Hungarian method for the given cost matrix. The first method is, I'll go with the row reduction. In row reduction, select the first element. Select the minimum element in every row. So in the first row, the minimum element is 12. We have 12, 30, 21 and 15. The minimum element is 12. Now I'll subtract other elements with the help of 12. So now I'll subtract it from 12. So 12 minus 12 is 0. Next 30 minus 12. So now 30 minus 12 is 18. Next 21 minus 12 is 9. 15 minus 12, it is 3. This is the first row. Similarly, repeat the same process for the second row. See, this is my second row. The minimum element is 3. I'll subtract from 3. Minimum element is 9. I'll subtract the other elements by 9. So 18 minus 9 is 9. 33 minus 9 is 24. 9 minus 9 is 0. 31 minus 9 is 20. Similarly, I go to third row. Minimum element is 21. I subtract from 21. 44 minus 21 is 23. 25 minus 21 is 4. 24 minus 21, it is 3. 21 minus 21 is 0. Similarly, I go to third row, fourth row. The elements are 23, 30, 28, 14. The minimum element is 14. I will subtract the other elements by 14. So 23 by 14. 23 minus 14 is 9. 30 minus 14. It is 16. 28 minus 14. This is 14. And 14 minus 14 is 0. This is row reduction. I reduce the row. Similarly, you need to go for column reduction. That's the second step. I go for column reduction. Let us see what will happen in column reduction. Look at the column wise. So in the first column, the minimum element is 0. So I'll subtract other elements by 0. So this becomes 0 minus 0 is 0. 9 minus 0 is 9. 23 minus 0 is 23. 9 minus 0 is 9. And what is the second column? The minimum element is, this is my second column. The minimum element is 4. So we need to subtract. 18 minus 4 is 14. And 24 minus 4 is 20. 4 minus 4 is 0. 16 minus 4 is 12. Similarly, go to third column. Minimum element is 0. I'll subtract from 0. 9 minus 0 is 9. 0 minus 0 is 0. 3 minus 0 is 3. 14 minus 0 is 14. Similarly, I go to the fourth column. Minimum element is 0. I'll subtract from 0. So 3 minus 0 is 3. 22 minus 0 is 22. 0 and 0. 22 minus 0 is 22. 0 minus 0 is 0 and 0 minus 0 is 0. This is column reduction. Next, I go to allocation. The next step is allocation. See, in this column, in the allocation, give the preference, first give the preference for rows, then column. So identify the row having minimum 0. Look at the first row. In the first row, this is my first row. In this row, we have 0, 14, 9, and 3. The first row having single 0. Therefore, I will allocate for this 0 and I will cancel the corresponding column. So for this row, for this cell, for this 0, the corresponding column is first column. I will cancel the corresponding column. So now I will allocate 0 and I will cancel the first column. I will cancel the first column. So I will cancel this column. I will cancel this column. Now look at the second row. Go to the second row. So in the second row, you have this 0. These are the elements in the second row having single 0. So now I cancel this one. I will allocate this 0 and I will cancel the corresponding column. So in my allocation is for this 0 and I will cancel the corresponding column. This is the corresponding column. Now I will cancel it. So I will cancel this corresponding column. Then go to the third row. Look at the third row. In third row, you have 0 and 0, 2 zeros. So I will not allocate. Go to the fourth row. Have 12 and 0. Fourth row having single 0 element. So I allocate this 0 and I cancel the corresponding column. Now I allocate this 0 and I cancel the corresponding column. I cancel this column. Next, go to the column wise. So I completed a row wise allocation. Then I go to the column wise allocation. You have only one column, that is the second column. So this column having single 0. This column having single 0. So now I allocate this column and I will cancel the corresponding row. Now this is my allocated element and I'll cancel the corresponding row. So I'll cancel this row. This is my corresponding row. So now since we don't have any zeros in the cost matrix, so it is a time to check whether the solution is optimum or not. To check the optimum solution, find out the number of allocations in this matrix. You have 1, 2, 3, 4. There are 4 allocations, and look at the size of the matrix. Size of the matrix is also 4. Therefore, the solution is optimum. And also we can see the optimum assignment for this solution. So we need to write the I conclude that since the number of allocations equal to the size of the matrix. The size of the matrix, therefore the solution is optimum. Therefore the solution is optimum. We need to find the optimum solution. And look at the allocation, optimum allocation. So that is 1 to J1, then you have 2 to J3, and next one is you have 3 to J2, 3 to J2, then look at 3 to J2, then 4 to J4, 4 to J4. 4 to J4. This is the optimum assignment for this combination for men and while assigning man to that particular job, this will be the optimum assignment. So what about the optimum cost? See 1 to J1. 1 to J1 is 12 rupee, and 2 to J3. 2 to J3 is 9 rupee. Then 3 to J2. So 3 to J2 is 25 rupees. Then 4 to J4. 4 to J4 is 14 rupees. So therefore the total is, so we can cross check the total cost. Total optimum cost. Optimum cost is, just add this one, 12 plus 9 plus 25 plus 14. So we are getting 60 rupees. So this is the total optimum cost. Okay. So like that, we need to solve the assignment problem to determine the optimum assignment as well as optimum cost by applying Hungarian assignment method. This is one type of problem you will find in the assignment problem. And similarly, I'll take one more problem. Let's see, in this problem, directly we are getting the optimum solution because number of allocations is equal to the size of the matrix. If number of allocation is not equal to size of the matrix, so how do you solve those types of assignment problems by using Hungarian assignment method? Let us see one more problem. So I'll take this problem, solve the following assignment problem by Hungarian assignment technique or Hungarian assignment method. So machine and jobs are given. The machines we need to assign for, there are 4 machines and 4 jobs. So we need to assign machine for that particular job. Okay. And the cost is given. This is a cost matrix. While assigning M1 to J1, we need to spend 14 rupees. Similarly, M1 to J2, we need to spend 5 rupees. That is a cost, expenditure cost. We need to spend for the assigning M1 with J2. So that cost matrix is given. Now let us see how to solve this type of problem. So while solving Hungarian method, remember the matrix should be a square matrix. Cost matrix should be a square matrix. Now look at this in this problem. You have 1, 2, 3, 4 rows and 4 columns. Therefore, the matrix is square matrix. This matrix is square matrix. So then we need to proceed with Hungarian assignment problem. Let's apply row reduction, column reduction, and allocations. So now I'll apply these 3 conditions: row reduction, column reduction, and allocations. Let's see, row reduction, column reduction, and allocations. So now first I'll identify the minimum element in the first row. Minimum element in the first row is 5. We need to subtract 14 minus 5, 5 minus 5, 8 minus 5, and 7 minus 7 to get the values in this table, in the cost matrix table, by applying row reduction. Let us take 14 minus 5. 14 minus 5 is 9. 5 minus 5 is 0. 8 minus 5 is 3. 7 minus 5 is 2. Then similarly, I'll go to the second row. In the second row, the minimum element is 2. I'll subtract other elements by 2. 2 minus 2 is 0. 12 minus 2 is 10. 6 minus 2 is 4. And 5 minus 2 is 3. Similarly, I'll go to the third row. In the third row, you have 7, 8, 3, and 9. The minimum element is 3. So we need to subtract other elements by 3. So 7 minus 3. It is 4. 8 minus 3, it is 5. 3 minus 3 is 0. And 9 minus 3, 6. Similarly, I'll go to the next row, fourth row. The minimum elements are 2, 4, 6 and 10. So these are the elements in the fourth row. The minimum element is 2. So we need to subtract other elements by 2. So 2 minus 2 is 0. 4 minus 2 is 2. 6 minus 2 is 4. And minus 2 is 8. So I applied row reduction technique. This is a row reduction technique I applied for this cost matrix, and this is the new matrix, new cost matrix. Similarly, we need to apply for column reduction. I'll go to the second step, is column reduction. Let us see this table. So now, look at the column wise. In the first column, identify the minimum element. Minimum element is 0. I subtract other elements by 0. So 9 minus 0 is 9. 0 minus 0 is 0. 4 minus 0 is 4. 0 minus 0 is 0. Similarly, go to the second column. In the second column, the minimum element is 0. I subtract other elements by 0. So this is 0 minus 0 is 0. 10 minus 0 is 10. 5 minus 0 is 5. And 2 minus 0 is 2. Similarly, go to the third column. These are the elements in the third column. Minimum element is 0. I subtract other elements by 0. So 3 minus 0 is 3, and 4 minus 0 is 4, 0 minus 0 is 0, and 4 minus 0 is 4. And similarly, in the fourth column, the minimum element is 2. So we need to subtract the other elements by 2. So 2 minus 2 is 0, and 3 minus 2 is 1, 6 minus 2 is 4, and 8 minus 2 is 6. 8 minus 2 is 6. So this is a column reduction. I applied column reduction. Next step is, so we need to go for allocation. This third step is very important for this matrix. So while while allocating, first give the preference for row allocation, then go for column allocation. So in a row allocation, identify the row having single allocation, single zero element in the row. Look at the first row. In the first row, we have 2 zeros. This one and this one I will not allocate. Go to the third row, next row, second row. In the second row, we have 1 0, single 0. Therefore, I will allocate for this element and I will cancel the corresponding column. So now my allocation is for this element. Allocate this element and I will cancel the corresponding column. So this is my column. This is my corresponding column. This is my corresponding column. I cancel the corresponding column. Next, go to the third row. Third row again, the elements in the third row are 5, 0, and 4. So allocate this element. Allocate this element. I allocate this element and I'll cancel the corresponding column. So my corresponding column is third column. I'll cancel this third column. And similarly, go to the fourth row. In fourth row, you have 2 and 6, no zeros. So next, I'll give the preference for the column wise. Look at the column wise. In the first column, the elements in the second column, the elements are 0, 10, 5, and 2. So I have single 0 in the second column. So I allocate this column. I allocate this element. So now I am allocating this element and I will cancel the corresponding row. So this is my corresponding row. I will cancel the corresponding row. Now go to the next column. In this column, we don't have any zeros. So now this is the time to check the optimality. Since the number of allocations are 3, but size of the matrix, look at the size of the matrix, it is a 4 by 4 matrix. Therefore, the solution is not optimum. Since the size of matrix, since the number of allocations, is not equal to size of the matrix. Size of the matrix, therefore solution is not optimum. Therefore the solution is not optimum. Not optimum. How to get the optimum solution? How to get the optimum solution? It's very important. How to find the optimum solution? To find the optimum solution, to find this optimum solution, first identify, see here this 10, 2, 5, 1, 4, 6. So these elements are not cancelled. So in these elements, select the minimum element. So minimum element is 1. Now subtract the uncancelled elements by 1. Then this becomes here 10. 10 minus 1 is 9. Then 5 minus 1 is 4. 2 minus 1 is 1. Then look at this uncancelled elements. 1 minus 1 is 0. 4 minus 1 is 3. 6 minus 1 is 5. 6 minus 1 is 5. Then you will find the intersection lines. See here 9 having row and column intersection. 3 having horizontal vertical intersection for element number 3 as well as for element number 9. For these two elements, I will add 1. Then this become 9 plus 1 is 10, and this become 3 plus 1 is 4. Then next step is write down the remaining element as it is. So this becomes 0, this becomes 4, this becomes 0, and this becomes 0, and this become 4, this becomes 0, this becomes 4, and this become 0. This is my new matrix. This is my new matrix. See here I applied row reduction. For the year I applied column reduction. I'll allocate. Then we didn't get the optimum solution. Then again I will reallocate. I'll do reallocation. I'll do reallocation to get the optimum solution. This is a reallocated elements in the cost matrix. Now, again try to allocate the cells in the modified cost matrix, and we will see whether we will get the optimum solution or not. So identify the row having single 0. First row having 2 zeros. Second row 2 zeros. Third row 1 0. So allocate this element. And I will cancel the corresponding column. So I will locate this element and I will cancel the corresponding column. So my column is, this is my corresponding column. I cancel this column. Go to third last row, fourth row. The elements are 0, 1 and 5. You have single 0. I will allocate this element and I will cancel the corresponding column for that element. So now my allocation is for this element. Allocate this element and I will cancel the corresponding column. So my corresponding column is, this is my corresponding column. This is my corresponding column. Next, row wise I completed the allocation with respect to row wise I completed. Then I go to column wise. Look at this second column. Second column having single 0, 0, 9, 4 and 1. You have single 0. So I allocate this 0. Allocate this 0 and I'll cancel the corresponding row. I'll cancel the corresponding row. This is my corresponding row for this 0. Then go to the third column, already assigned. Go to the fourth column. In the fourth column, the elements are 0, 3, and 5. So I have single 0. Allocate this 0. Allocate for this 0. And I'll cancel the corresponding row. We need to cancel the corresponding row. So I'm cancelling this particular row. Next check, is there any other zeros, uncancelled zeros in the cost matrix? We don't have uncancelled zeros in the cost matrix. So now we can check, this is the time to check the optimality. We have 4 allocations and look at the size of the matrix. The size of the matrix is 4 by 4. Therefore, the solution is optimum. You can write the comment, since the number of allocations is equal to the size of the matrix. Size of the matrix, therefore the solution is optimum. Therefore, solution is optimum. Now find out what is the optimum solution and what is the optimum assignment. Say optimum assignment is say M1 to J2, M1 to J2, M1 to J2, M1 to J2. Then similarly, this is M2 to J4, M2 to J4, M2 to J4. Then I'll go to M3 to J3, M3 and J3, M3 and J3. And last one is you have M4 and J1, M4 and you have J1, which is J1. So this is the optimum assignment of machines with respect to jobs, and the corresponding cost or M1 J2. M1 J2 is 5 rupees and M2 J4, this is M2 and J4 is 5. This is also 5 rupees. And M3 J3, M3 and J3 is 3 rupees. Then M4 and J1 is 2 rupees. So my total cost is optimum cost. Optimum cost is, just add this one, 10, 13, 14 and 15, 15 rupees. 15 rupees will be the optimum cost for the given cost matrix. So with this, I conclude today's session, and those who are new for this channel, I request you to subscribe this channel and like the video. Thank you so much.